Let me ask you something. What happens when you blow out a candle? You watch the flame disappear. The wax has been melting for an hour, dripping down the sides, pooling at the base. The wick turns black and curls over. And if you come back to that candle a few days later, there is almost nothing left. A little stub of wax, a blackened string, the thing that used to sit on your kitchen table, solid, waxy, real, is mostly gone. So I want to know, where did it go? If I asked 100 people on the street, 90 of them would say something like it burned up. They say it with total confidence, as though that phrase explains something. But watch out, because burned up is not an explanation. It is a description of what your eyes saw. It tells you nothing about what actually happened. And I am going to take this little question about a candle and follow it all the way down, because the answer is going to lead us to something that I think will genuinely change the way you think about life and death and the people you have loved. So let us start with the candle. Real simple. A candle is made of paraffin wax, which is a chemical made of carbon and hydrogen atoms linked together in long chains. When you light the wick, you are providing enough thermal energy to break those molecular bonds. The carbon atoms freed from the wax immediately grab onto oxygen molecules from the surrounding air and form carbon dioxide. The hydrogen atoms do the same thing and form water vapor. And the energy that was stored in those chemical bonds, the energy that held the wax together, gets released as heat and light, that yellow glow you see. That is, atoms in the process of rearranging themselves. The flame is not a thing, it is an event. It is chemistry happening fast enough to emit visible light. And here is the key. When the candle is done, when there is nothing left but a stub and a memory, nothing has actually disappeared. Not one atom. Every carbon atom that was locked in that paraffin is now floating around the room as part of a carbon dioxide molecule. Every hydrogen atom is now part of a water molecule hanging in the air. The energy that was stored in the wax is now warming the walls and the ceiling and the air and your skin. If you had incredibly sensitive instruments, you could track every single atom and every single unit of energy and account for all of it. The candle is not gone. It is rearranged. It is everywhere. Now, somebody in the audience is going to say, but Feynman, I looked around the room and I did not see any carbon dioxide or water vapor. The candle is just gone. And I say, of course you did not see it. You cannot see individual molecules. But they are there. If you took the air in the room and ran it through a chemical analyzer, you would find slightly more carbon dioxide and slightly more water vapor than there was before you lit the candle. The mass would balance out to the microgram. The chemistry is exact. The accounting is perfect. This is not a metaphor. I want to be absolutely clear about that. This is not a poetic way of talking about loss. This is one of the most fundamental and well-tested facts in all of physics. It has a name, the conservation of mass energy, and it was first pinned down by a French chemist named Antoine Lavoisier in the 1770s. Lavoisier did something very clever. He sealed chemical reactions inside glass containers, weighed everything before and after, and discovered that the total mass never changed. Not by a hair. Burning, rusting, fermenting, dissolving, it did not matter. The total weight of the stuff going in was always exactly equal to the total weight of the stuff coming out. He said in so many words, nothing is lost, nothing is created, everything is transformed. And 250 years of physics since then has done nothing but confirm this more and more deeply. We have tested it with chemical reactions and nuclear reactions and particle collisions. We have tested it at temperatures close to absolute zero and at temperatures hotter than the center of the sun. We have tested it in laboratories on Earth and in observations of galaxies billions of light years away. The books always balance. Always. There has never been a single verified exception. Not one. When you... And by the way, Lavoisier paid dearly for his other activities. He was a tax collector as well as a scientist, and during the French Revolution, the revolutionaries arrested him and sent him to the guillotine. The judge reportedly said that the Republic had no need of scientists. They cut off his head, and a colleague remarked that it took them only a moment to cut off that head, but France may not produce another like it in 100 years. The atoms in Lavoisier's body, the man who proved that atoms are never destroyed, were themselves redistributed, back into the soil of France, into the grass, the crops, the water, the air. His own body obeyed the law he had discovered. There is a kind of bitter poetry in that, but the physics holds regardless of the poetry. So that is the first layer. And you are probably thinking, all right, fine, atoms persist, Conservation of mass. I learned that in school. What is the big deal? And if this were the whole story, you would be right to shrug. But I have barely started. Let me push this further. Think about a person. Somebody you loved. Your mother. Your grandfather. Someone who mattered to you. When they were alive, their body was made of atoms. Roughly 7 billion of them. Give or take. Carbon, oxygen, hydrogen, nitrogen, calcium, iron, phosphorus, and traces of a couple dozen other elements. A recipe if you want to think of it that way. About 65% oxygen by mass, 18% carbon, 10% hydrogen, 3% nitrogen, and a scattering of everything else. Where did those atoms come from? They were not minted fresh the day that person was born. Every single one of them was already ancient, billions of years old. The hydrogen atoms in their body are the oldest things in the universe. They were created in the first few minutes after the Big Bang, roughly 14 billion years ago, when the universe was a blinding hot soup of particles and radiation. Those exact hydrogen atoms, the ones that ended up in your mother's body, have been around since the very beginning of time. The heavier elements have a different origin story. The carbon in her bones, the oxygen in her blood, the calcium in her teeth, those were forged inside the cores of massive stars that lived and died long before our sun was born. Here is how that works. A large star, something maybe 8 or 10 times the mass of our sun, spends millions of years fusing hydrogen into helium in its core. When the hydrogen runs low, it starts fusing helium into carbon, then carbon into oxygen, then oxygen into neon, neon into silicon, silicon into iron. Each stage burns hotter and faster than the last. By the time the star is fusing silicon into iron, it has only days left to live. And then the core collapses. The outer layers come crashing inward and bounce off the incompressibly dense core, and the whole thing explodes outward in a supernova. A single star dying, and in its death it scatters those freshly forged elements, carbon, oxygen, calcium, iron, across light years of space. Some of those atoms drifted into a cloud of gas and dust that, about 4.5 billion years ago, collapsed under its own gravity to form our solar system. They got swept into the Earth. They cycled through rocks and oceans and volcanoes in the atmosphere. They were taken up by microbes, by plants, by animals. They worked their way through the food chain for billions of years, and eventually some of them, a tiny fraction, ended up assembled into the body of someone you loved. I want you to appreciate the scale of that journey. A carbon atom in your grandmother's body was created at a temperature of about 600 million degrees, inside a star that may have been 1,000 light years from where the Earth would eventually form. That star exploded. The carbon atom was blasted into space at thousands of miles per second. It drifted for millions of years through the interstellar medium. It was swept into the collapsing cloud that became our solar system. It was incorporated into a rocky planetesimal that smashed together with other planetesimals to build the Earth. It spent billions of years locked in rock or dissolved in ocean water, or drifting through the atmosphere as carbon dioxide. It was absorbed by a plant, eaten by an animal, eaten by another animal, washed into the soil, taken up again by a different plant, over and over and over, cycling through the biosphere for eons. And then, for a few decades, it was part of a human being who knew your name and loved you. That atom had no idea any of this was happening, of course. Atoms do not have ideas. But the path is real, the journey is physically traceable. And it is staggering to me that people can know this and still think the universe is meaningless. So already there is something astonishing here that most people walk right past. Those atoms were not hers, not in any permanent sense. She borrowed them. She borrowed them from the Earth for 60 or 70 or 80 years, rearranged them into a breathing, thinking, laughing human being, and then when she died, she returned them. Every last one. The carbon went back into the soil or the atmosphere. The water went back into the cycle. The calcium went back to the ground. The iron went back into the earth. Nothing was lost. Nothing was taken off the ledger. And those atoms are still here. Right now. On this planet. In the soil under your feet. In the trees outside your window. In the air you are breathing. In the ocean. In the crops growing in the field. In the body of a child being born today on the other side of the world. Some of those atoms, statistically, inevitably, are in you. You are breathing in atoms that were once part of everyone who has ever lived. Not metaphorically, literally. There are so many atoms in a single human body, and those atoms recirculate so thoroughly over time that the arithmetic makes it practically certain that you carry atoms from every person who lived more than a few hundred years ago. Julius Caesar, Cleopatra, your great-great-grandmother. The math is inescapable. And here is something else that ought to shake you a little. It is not just the dead who give their atoms back. You are doing it right now, while you are alive. Every time you exhale, you release carbon dioxide molecules that contain carbon atoms that were moments ago part of your body. Every time you sweat, you release water that was part of your blood. Your digestive system sheds its lining every few days. Your red blood cells are replaced roughly every 4 months. But over the course of about 7 to 10 years, you have turned over nearly every atom in your body. The you sitting here right now is made of almost entirely different stuff than the you from a decade ago. So even the idea that you are a fixed collection of atoms is an illusion. You are a pattern that matter flows through, like water flowing through a whirlpool. The whirlpool is real, it has a shape, it persists. But the water passes through it continuously. The atoms you are made of today were part of the soil and the grass and the animals and the rain 6 months ago. And the atoms that were part of you 6 months ago are now part of the soil and the grass and the animals and the rain. You are not a thing, you are a process. A beautifully organized, staggeringly complex, temporary arrangement of borrowed stuff. And that is true of everyone you have ever loved. They were processes too. Whirlpools in the flow of matter and energy. And when the whirlpool stopped, the water did not disappear. It just joined the larger current. Right, so now comes the objection. And it is a good one. It is a good one. You are sitting there thinking, okay, Feynman, the atoms stick around. Very nice. But atoms are generic. A carbon atom is a carbon atom. What made my grandmother? My grandmother was not the atoms. It was the arrangement, the pattern. The specific way those atoms were organized into cells and tissues and organs and a brain that could think her thoughts and remember her memories and love the people she loved. And that pattern is destroyed when someone dies. The arrangement scatters. The information is lost. That is a smart objection. Oh, and if you had asked me that question 100 years ago, I would have had to admit that you were right. But you are asking it now. And in the last century, we have learned something about information that changes the entire picture. But before we get to that, I want to slow down and talk about energy. Because there is a second conservation law separate from the conservation of mass, and it matters here. The first law of thermodynamics says that energy cannot be created and cannot be destroyed. It can only change from one form to another. Kinetic energy becomes thermal energy. Chemical energy becomes light. Electrical energy becomes sound. But the total amount never changes. This law is as ironclad as any principle in science. Nobody has ever found a loophole. Nobody has ever observed a violation. It holds in every domain, at every scale, under every condition we have ever examined. Now think about a living person. Every thought your grandmother ever had was an electrical impulse traveling along a nerve cell. A small burst of energy, ions flowing through channels in a membrane, creating a voltage that raced along an axon. Every beat of her heart was a muscular contraction, powered by chemical energy stored in a molecule called ATP. Every word she spoke was a vibration of her vocal cords that sent pressure waves through the air. Every warm embrace she ever gave you was thermal energy flowing from her skin to yours. When she died, not one unit of that energy disappeared. So the electrical activity in her brain slowed and stopped, but the energy did not vanish. It was converted into heat. The chemical energy in her cells was gradually released through decomposition and absorbed by the surrounding environment. The thermal energy of her body radiated outward into the room, the ground, the sky. The sound waves of her last breath spread outward through the air, losing amplitude, getting fainter and fainter, but never reaching exactly zero, because energy does not wink out of existence. Every joule of energy that ever powered a single moment of her life is still out there, transformed, diluted, dispersed across an inconceivably large number of particles and photons, but present. The first law guarantees it. The universe keeps meticulous books, and the ledger has never once failed to balance. Let me make this more concrete. Think about a specific moment. Say your grandmother laughed one afternoon in the kitchen. That laugh was a physical event. Her diaphragm contracted, pushing air up through her larynx. Her vocal cords vibrated at specific frequencies, producing sound waves that radiated outward in every direction. Those sound waves hit the walls of the kitchen, the furniture, the window glass, your eardrums. Each surface absorbed some of the energy and reflected some. The absorbed energy became a tiny amount of heat, warming each surface by an immeasurably small fraction of a degree. That thermal energy then radiated outward as infrared photons which traveled through the walls, through the roof, out into the sky. Some of those photons left the atmosphere entirely and are still traveling through space right now, moving outward at the speed of light, carrying with them a faint, impossibly faint trace of that laugh. I know that sounds crazy, but it is simple physics. Sound becomes heat. Heat becomes radiation. Radiation travels, and energy is conserved at every step. There is no point in the chain where the energy says, well, I have had enough, and winks out of existence. It does not do that. It cannot do that. So now we have atoms that persist and energy that persists. But you are still holding on to that objection about the pattern, the arrangement, the information. And I do not blame you, because that is where the real question lives. Death does not destroy atoms. Death does not destroy energy. Does death destroy information? And the answer, according to the deepest theory of nature we possess, is no. It does not. It cannot. The laws of physics forbid it. Let me explain this carefully because it is the most important part of everything I am going to tell you today. First, I need you to understand what physicists mean by information. We do not mean meaning. We do not mean stories or memories in the sentimental sense. We mean something much more precise. Information, in physics, is the complete description of the state of a system. Every position, every velocity, every spin, every quantum number of every particle. If you have that description, you have everything. You can, in principle, run the laws of physics forward and predict the future. You can run them backward and reconstruct the past. The information is the key to time. Let me give you a simple example to build your intuition. Imagine a deck of 52 cards in a specific order. That order is the state of the deck. That is the information. If I shuffle the deck, the cards rearrange. The new order looks random. It looks like the original order has been destroyed, but it has not been. If you knew the exact shuffling procedure, every cut, every riffle, every card that went where, you could reverse the procedure and recover the original order. The information was not erased by the shuffle. It was redistributed. It is still there, encoded in the new arrangement, recoverable if you know the transformation that was applied. Now imagine I shuffle the deck 1,000 times, 10,000 times, 1,000,000 times. After 1,000,000 shuffles, the order looks completely random. You would never guess what the original arrangement was just by looking at it. But here is the thing. If the shuffling procedure is deterministic, if every shuffle follows definite physical rules, then the original order is still encoded in the current arrangement. It is just very, very deeply buried. You would need to know the full history of every shuffle to extract it. But it is there. In classical physics, the physics of Newton, the state of a system is described by the positions and velocities of all its particles. If you know those numbers precisely, you can predict the future. You can also reconstruct the past. The equations work the same in both directions. Run the clock forward, and the particles move to new positions. Run the clock backward, and they return exactly to where they started. This is called time reversal symmetry, and it is built into Newton's laws. Quantum mechanics takes this even further. In quantum mechanics, the state of a system is described by something called a wave function. The wave function is a mathematical object that encodes everything there is to know about a physical system. It encodes probabilities, correlations, entanglements, superpositions, the whole works. And the wave function evolves in time according to the Schrödinger equation, which has a property that physicists call unitarity. Unitarity means, in plain language, that the evolution preserves all the information in the system. No information leaks out. No information is erased. Every quantum state evolves into a unique new quantum state, and the process can always be reversed. Think of it like a very elaborate code. You take a message, you run it through an encoding machine, and you get out an encoded message that looks nothing like the original, scrambled, unrecognizable. But the encoding is one-to-one. Every input maps to a unique output. So you can always run the machine backward and recover the original message perfectly without losing a single character. That is what unitarity means. The universe is an encoding machine that never loses a single bit. This is not a suggestion. It is not a philosophical preference. It is a mathematical requirement. If you break unitarity, quantum mechanics collapses. The probabilities stop adding up to 100%. The theory becomes internally contradictory. This is why physicists guard unitarity so fiercely. It is not a feature of quantum mechanics. It is the load-bearing wall. Pull it out and the whole building comes down. No. So what does this mean for a person? It means the complete quantum description of every atom, every electron, every photon, every interaction that was part of your grandmother. All of that information still exists somewhere in the universe. And it was not erased when she died. It could not have been erased. The Schrödinger equation does not have a delete function. It can scatter information across billions of particles. It can scramble it into correlations so complex that no conceivable technology could ever untangle them. But it cannot destroy it. It cannot make it as though it never was. Let me give you an analogy that might make this more vivid. Imagine you write a love letter on a piece of paper. Very personal. Every word chosen with care. Now imagine you tear that letter into 1,000,000 tiny pieces, smaller than grains of sand, and scatter them from an airplane over the Pacific Ocean. Practically speaking, that letter is gone forever. Nobody is ever going to recover it. But is the information destroyed? No. Every fragment is still somewhere, floating, sinking, being carried by currents. Every ink molecule is still bonded to a fiber of paper. If you had godlike patience and godlike instruments that could track every particle in the ocean, you could in principle find every piece, reassemble them, and read the letter word for word. The destruction was practical, not fundamental. The information was scattered, not erased. That is what death does to the quantum information of a person. It tears the letter into fragments and scatters them into the ocean of the physical world. It makes recovery practically impossible, beyond any technology we can imagine. But it does not destroy a single word. There is a name for this process in quantum physics. It is called decoherence. When a quantum system interacts with its environment, when a molecule bumps into other molecules, when a photon gets absorbed by a wall, the information about that system does not disappear. It spreads. It leaks into the environment. It gets entangled with more and more particles. And the more particles it entangles with, the harder it becomes to read. It is like writing a message in ink, then dropping the paper into a swimming pool. The ink dissolves. The molecules spread through the water. The message becomes unreadable to anyone looking at the pool. But every ink molecule is still there, and the information about where it came from is still encoded in its position and its correlations with every water molecule it has touched. The pool has absorbed the message. It has not erased it. Decoherence is the reason death looks like erasure, even though it is not. When a person dies and their body returns to the environment, the quantum information that described them spreads into the soil, the air, the water, the radiation field. It entangles with so many other systems so quickly that any practical ability to read it vanishes almost instantly. From a human perspective, the information is gone. From the perspective of the fundamental laws, it is merely relocated, scattered, encoded in the vast, incomprehensibly complex web of quantum correlations that we call the environment. But the laws do not care about our perspective. They care about what is actually happening. And what is actually happening is that nothing is being erased. You want to know how seriously physicists take this principle? Seriously enough that it caused one of the biggest intellectual wars in the history of science. And the war was about black holes. In the early 1970s, Stephen Hawking made one of the most remarkable calculations in the history of theoretical physics. He combined quantum field theory with general relativity, Einstein's theory of gravity, and showed that black holes are not perfectly black. They glow faintly. They emit a thin mist of radiation, now called Hawking radiation, generated by quantum effects near the event horizon, the boundary beyond which nothing can escape. This radiation carries energy away from the black hole, and because the black hole is losing energy, it is losing mass. Very, very slowly, over timescales longer than the current age of the universe. But inexorably, a black hole, Hawking showed, will eventually evaporate completely, shrink down to nothing and vanish. And then Hawking asked the question that started the war: what happened to the information? Suppose a book falls into a black hole, a complete encyclopedia, every page, every word, every diagram. The black hole swallows it, grows slightly heavier, and then slowly evaporates over trillions upon trillions of years, radiating away its mass as a faint glow of thermal particles. Hawking calculated the properties of that thermal radiation and concluded that it was perfectly random, structureless. It carried no imprint whatsoever of what had fallen in. A book and a lump of coal of the same mass would produce identical Hawking radiation. The information about the book, Hawking argued, was simply gone, destroyed, erased from the universe. This was a direct attack on unitarity. If Hawking was right, then information could be destroyed. The principle that every quantum process is reversible would have a gaping exception, and the physics community split. And on one side stood Hawking and a group of relativists who trusted the geometry of black holes. They were prepared to accept that information could be permanently lost. On the other side stood virtually every quantum physicist alive, led most fiercely by Leonard Susskind at Stanford and Gerard de Hooft in Utrecht. Their position was simple and absolute. Information cannot be destroyed. Period. If your calculation says otherwise, then your calculation is missing something. Go back and look harder. The argument consumed 3 decades. It was fought at conferences in Santa Barbara and Cambridge and Dublin. It was fought in journal papers and in popular books. Hawking and Kip Thorne made a formal bet with John Preskill, wagering an encyclopedia that information was truly lost in a black hole. The stakes were modest, but the symbolism was enormous. This was a bet about whether the universe keeps perfect records. The resolution came through a series of breakthroughs in string theory and quantum gravity. The most important was a result by Juan Maldacena in 1997 called the ADS-CFT correspondence. Without going into the technical details, Maldacena showed that certain theories of gravity, theories that include black holes, are mathematically identical to quantum theories that live on the boundary of that gravitational space, and those boundary theories are manifestly unitary. Information is preserved in them by construction. If the two descriptions are really the same physics written in 2 different languages, then information must also be preserved in the gravitational version. The black hole cannot erase it. More evidence accumulated. Detailed calculations showed that the information comes back out, encoded in subtle correlations between the particles of Hawking radiation. Not in any simple, readable way, scrambled beyond all practical recovery, but fundamentally present, complete, intact. In 2004, Hawking conceded. He stood up at a scientific conference in Dublin, Ireland, and announced that he had been wrong. Information is not destroyed by black holes. He paid off his bet with Preskill. He gave him a baseball encyclopedia. And the audience laughed, but the significance was not funny at all. One of the greatest minds in theoretical physics had just acknowledged that the universe guards its information more jealously than anyone had imagined. The implications radiated outward through the physics community. If a black hole cannot destroy information, then we live in a universe with no eraser. Think about that for a moment. A black hole takes the very geometry of space and curves it into a trap. It pulls matter past a point of no return. It crushes that matter down to densities that our best theories cannot describe. And even that is not enough to delete information from nature's books. The information survives. It comes back out, encrypted in the quantum correlations of the radiation the black hole emits over its lifetime. It is as if you threw a library into a furnace and the smoke that rose spelled out every word of every book if only you could read the pattern precisely enough. Susskind called it the Black Hole War. And he was not exaggerating. The stakes were that high, because if information could be destroyed, the entire framework of quantum mechanics, the most successful physical theory ever constructed, would be compromised. And if it could not be destroyed, not even by the most extreme gravitational environment the universe can produce, then information conservation is not just a nice rule. It is absolute, unbreakable, as fundamental as anything in physics. Think about what that means. A black hole is the most extreme object in the known universe. It is a region where gravity is so strong that space itself curves inward, and nothing, not even light traveling at 186,000 miles per second, can climb back out. If even a black hole, the ultimate cosmic shredder, cannot permanently erase information from the universe, then what can? The answer, as far as the deepest physics we have can tell, is nothing. Nothing in this universe has the power to permanently destroy information. The ledger is always complete. So let me gather the threads and show you what we have built. Your grandmother's atoms are still here on Earth, cycling through the soil, the water, the atmosphere, the bodies of other living beings. The energy that powered every moment of her life, every thought, every heartbeat, every laugh, is still present in the universe, dispersed and transformed, but conserved to the last jewel. And the quantum information that described her complete physical state, every correlation, every entanglement, every detail of her molecular arrangement, is still encoded in the quantum state of the cosmos, scrambled into the correlations between billions upon billions of particles and photons, but never erased. Nothing about it was thrown away. And the universe does not work like that. It does not discard things. It rearranges them, it transforms them, it scatters them, but it saves everything. And now I want to take you one more step, one final layer, because there is a mathematical theorem in physics that says something even more startling. It is called the Poincaré recurrence theorem, and it was proved by the French mathematician Henri Poincaré in 1890. The theorem says this: take any physical system that occupies a finite region of space and has a fixed total energy. Let it evolve according to the laws of physics. Then, given sufficient time, the system will return arbitrarily close to any state it has previously occupied. Not sort of close as you like. Pick any precision you want, 1 part in a million, 1 part in a billion, 1 part in a trillion, and the system will eventually return to within that precision of its original state. Imagine you put a handful of marbles in a box and start shaking the box, and the marbles bounce around, constantly changing positions. There's a thing, but there are only so many marbles and only so much room. If you shake the box long enough, the marbles will eventually return very close to whatever arrangement they started in. The Poincaré theorem is the rigorous mathematical version of this intuition, extended to any physical system with finite size and fixed energy. Or think of it this way. Suppose you have a room full of air molecules, and at some particular moment, purely by chance, all the oxygen molecules happen to be in the left half, and all the nitrogen molecules happen to be in the right half. That is an extraordinarily unlikely arrangement. In the next instant, the molecules will mix, and within a fraction of a second they will be thoroughly scrambled. The room will look perfectly normal again. But Poincaré tells you if you wait long enough, not just a long time, but a staggeringly, incomprehensibly long time, all those molecules will again find themselves separated. Oxygen on the left, nitrogen on the right. The same arrangement will recur. And not just that arrangement. Every arrangement the room has ever been in will recur. Every arrangement it could ever be in will occur. The system explores every possible state, and in doing so must revisit old ones. How long would you have to wait? This is where your intuition fails you completely. For even a modest system, the recurrence times are numbers so staggeringly large that no analogy can convey them. For a box containing a few hundred gas molecules, the Poincaré recurrence time is already something like 10 to the power of 10 to the power of 20. That is not 10 to the 20th power. That is 10 raised to the power of a number that is itself 10 to the 20th power. A 1 followed by 100 billion zeros. The current age of the universe, roughly 14 billion years, is less than an eye blink on that scale. For a system as complex as a human body, with its 7 billion atoms, the recurrence time is so inconceivably vast that the number itself is essentially meaningless. It is not a number you could write down even if you used every atom in the universe as a digit. It is beyond big. It is beyond big. So let me be very clear, this is not something to wait around for. The recurrence time has zero practical significance. You will not live to see it. The sun will not live to see it. The universe as we know it will not persist long enough for even the simplest interesting recurrence to occur. But mathematically, the theorem is absolute. Given a finite system and enough time, every configuration that has ever existed must recur. The laws of physics do not forbid it. They require it. Now I owe you the caveats, because I believe honesty matters more than comfort, and you should know exactly where the solid ground ends and the open questions begin. First, the Poincaré recurrence theorem assumes a finite system with fixed energy. We do not know with certainty that the universe meets this condition. Observations suggest it might be finite, but cosmological models exist in which the universe is spatially infinite, or in which dark energy drives eternal expansion, diluting the energy density towards zero. In such a universe, the global recurrence might not apply. The honest answer, we do not know. We do not know. Second, the second law of thermodynamics says entropy tends to increase. Systems move from order toward disorder. A dropped glass shatters. The shards do not leap back together. And this is overwhelmingly true as a statistical tendency. But notice statistical. The second law is not a fundamental law like conservation of energy. It describes what is overwhelmingly probable, not what is absolutely certain. The Poincaré recurrence does not violate the second law. The recurrence simply occurs on timescales so vast that the second law appears ironclad for all practical purposes. Practically certain and absolutely certain are different claims. Physics respects the difference. Let me put it this way. If you shuffle a deck of cards 1,000,000,000,000 times, the chance of returning to the original order on any given shuffle is vanishingly small. But it is not zero. And if you shuffle forever, you must eventually hit it. The second law says, do not hold your breath. The recurrence theorem says, but do not say never. Third and most subtle. Quantum mechanics introduces genuine, irreducible randomness. The outcome of a quantum measurement is not determined by any hidden mechanism. It is fundamentally probabilistic. This means that even if the universe returned to a configuration very close to a previous one, the quantum events that followed might unfold differently. The arrangement of atoms might recur, but the story that plays out from that arrangement might branch in a new direction. The recurrence theorem brings back the stage. It does not guarantee the same play. Those are the caveats. They matter. Honest physics includes them. But now let me step back and tell you what I make of all of this. As a person who has spent his life staring at equations and trying to understand what nature is telling us, when someone dies, most people experience it as a subtraction. A person who existed no longer exists. A voice that spoke is silent. A face that smiled is gone. The grief is real. The absence is real. I would never minimize that for a moment. But the physics tells a different story about what actually happened to the stuff that person was made of. Physics says nothing was subtracted from the universe. Not a single atom. Not a single joule. Not a single bit of quantum information. The universe does not have a delete function. It has a transform function, a rearrange function, a scatter function, but never ever a delete. The atoms that shaped your grandmother's smile are out there right now, participating in something else. In a leaf catching sunlight, in a river carving through stone, in the body of a child on the far side of the world. The energy that powered her laughter is still propagating, absorbed and re-emitted and transformed 1,000,000,000 times over, but present, accounted for, obeying the first law as faithfully as it did the day she was born. And the quantum information that described every detail of her physical state is woven into the correlations of the cosmos, entangled with everything she ever touched, every photon that ever bounced off her face, every molecule of air she ever breathed. People sometimes tell me that physics is cold, that science strips meaning out of life, that equations have nothing to say about love or grief or what it means to miss someone. I have heard it 1,000 times, and each time I think they have it exactly backward. Because when I read what the equations actually say, I find them more moving than anything else I have encountered. Think about what we have actually established here, step by step. We started with a candle, with something so ordinary you would walk past it without a second thought. And by following the question honestly, by refusing to accept burned up as an answer, we arrived at the conclusion that the universe is a perfect bookkeeper that never loses a receipt. We did not assume this. We did not hope for it. We followed the evidence, layer by layer, from Lavoisier's sealed flasks to Hawking's capitulation in Dublin. And at every layer, the same message came through. Nothing is thrown away. The universe conserves. It preserves. It remembers. And this applies to everything, not just to candles, not just to stars, to people. To the ones who sat across from you at the dinner table, to the ones who held your hand when you were small, to the ones whose absence you carry like a stone in your chest. The physics says they are not gone. Not in the way you think. The stuff is still here. The energy is still here. The information is still here, scrambled, transformed, woven into the fabric of everything else. But here, the equations say the universe is a perfect memory, not as a metaphor, as a mathematical consequence of unitarity. Every event that has ever occurred has left an indelible record in the quantum state of the world. The sound of your mother's voice on a summer evening, the warmth of your father's hand, the way light reflected off the face of someone you loved on a day you cannot forget. None of it is gone. The vibrations spread out and faded and got absorbed and re-emitted, and every single interaction was recorded in the quantum correlations of the particles involved. The trail is unimaginably faint. No technology that will ever exist could follow it, but it is there. The universe remembers. Now let me address something directly, because the title of this talk makes a bold claim, and I owe you a precise accounting of what I mean. When I say physics says you will see your loved ones again, I do not mean you will see them at a gate or in a garden or across a room. That is a beautiful idea, and I have nothing against people who find comfort in it, but it is not what the physics describes. What the physics describes is something different, and I think in some ways more profound. You see your loved ones every day. You see them in the oxygen you breathe, because some of those molecules pass through their lungs. You see them in the carbon in the food you eat, because the carbon cycle has been mixing and redistributing those atoms since the day they returned to the earth. You see them in the warmth of the sunlight on your skin, because energy, all energy, is part of a single conserved quantity that their metabolism once borrowed and then returned. You see them in the quantum correlations of the world around you, because every interaction they ever had left a permanent mark on the entanglement structure of reality. This is not the reunion people dream about when they grieve. I know that. It does not replace the sound of a voice or the pressure of a hand, but it is not nothing. It is the universe doing the only thing it knows how to do with the matter and energy and information of a person who is here. It is the universe refusing to let any of it go. And there is something in that refusal that I find deeply unexpectedly moving. The universe, which has no sentimentality, no feelings, no agenda, which follows its laws with perfect mechanical indifference, nevertheless behaves as though nothing is disposable, as though everything matters enough to keep. Here is the thought I want to leave with you. Sit with it tonight. Let it keep you up if it wants to. We live in a universe that does not throw anything away. Not an atom, not a joule of energy, not a single quantum bit of information. Every person who has ever lived, every person you have ever loved, is still present in the physical fabric of reality. Not as a ghost, not as a spirit in a cloud, as atoms still cycling through the biosphere, as energy still warming and illuminating the cosmos, as information still encoded, however faintly, in the entanglement structure of the quantum world. If you want to call that a kind of immortality, I would not argue with you. It is not the kind with a forwarding address you cannot have another conversation, but it is real, it is physical, it is backed by the most tested mathematics and the most rigorously confirmed principles that human beings have ever discovered. The universe does not forget. The laws of physics give it no choice. So the next time you stand under the night sky and feel the weight of someone who is no longer beside you, remember this. The atoms in those stars above you and the atoms in your body were forged in the same furnaces. The energy flowing through you right now once flowed through them, and the information, the full quantum ledger of every person who has ever lived, is still woven into the structure of everything that exists. They have not been subtracted, they have been folded in, and the universe carries them forward as it carries everything without losing a single thread. I want to know what you think. If the universe truly is a perfect memory, if nothing is ever erased, does that change how you see the people you have lost? Tell me. I am very curious to hear